share. So there we go. It looks good. Let me try the full one. All right. Okay. Shall I start?
Yes, please.
Okay. So thank you very much for the kind invitation to this meeting. I'm a newcomer to HEFT, and it's a pleasure for me to meet this community. So I'm reporting on a project together with Stefan Bissmann, Cornelius Grunwald, and Kevin Kröninger, which are actually part of our experimental teams, except for Stefan in Dortmund. So this is not just synergetic in top and muti, it's actually a synergy between theory and experiment, and this has resulted in SMEFT fits. So a little bit of a start is we had a spring meeting of the German Physics Society, and there was a huge number of sessions in flavor physics. And when you look at all of this, I mean, there's a large number of experiments who will collect information on kaon physics, on B physics, on charm physics, some on both of these, and then of course Atlas CMS on bottom and top, and maybe also lighter flavors, and there are some future facilities that have also been covered. So if you are in flavor physics, it's a bit of a dream time now. So and it even doesn't stop here. If I'm sure you watch this, you are very well aware of that. We had, I mean, two anomalies that got strengthened over the past 3 weeks. There was the announcement of LHCb that RK, which measures the ratio of branching fractions BS mu mu versus B to SEE, at probes universality, it's off by more than 3 sigma in one single measurement. So this is what they call evidence. And there was, of course, G-2 of the muon. So together with all the other anomalies in the flavor sector, and I'm listing here just a few, the BM anomalies, G-2 and so on, then you would think, okay, roughly speaking, there's one common denominator, and it is there's something with leptons and low energy data. So that's a good thing to, I mean, invest as a phenomenologist or in model builders if you want to address these type of pattern that we are facing. And in particular, of course, it means that you would need to have some flavor in BSM model building, because this is what the data are hinting at. And this is also means you need to put some flavor into fits. So fits are, of course, a very good tool to do. I mean, there have been fits in the B sector and there have been fits in the other sector, but I think the main advantage of SMEFT is that you can combine everything and together with the top sector. So it becomes really, I mean, a laboratory also for flavor links. And that, of course, we just discussed that, okay, there is flavor, and if flavor is very general, then these Wilson coefficients, they become tensors in flavor space, and it becomes a bit of a large number of Wilson coefficients, and you need some structure. And the previous speaker actually made a very nice case that if you use some organizing principles, such as minimal flavor violation or a subset of that, then you can really structure these Wilson coefficients in flavor space. And of course, we learned from B physics studies in this weak effective theory that also there is no such thing as a truly model independent analysis. Even in weak effective theory, where the number of operators is significantly smaller than in SMEFT, just staying even in 6 dimensions, we are not fitting to the complete operators. We are fitting to those who have been identified at the most relevant one. And the others that are not covered in a fit, where we have some other arguments, how to constrain them and why our analysis in the subset is useful. So this type of fits in the B sector, this is ongoing precision physics. It's very successful. And even if it's not fully model independent, you make some assumption, you do make progress. And I think this is what you would need to do also in SMEFT. And I would say the big advantage of SMEFT that really can bring join communities and have a more global interpretation of this big amount of data that we are seeing, and there will be much more in the near future. So this is about top and beauty synergies, and the main example here is that there are these semi-leptonic 4 fermion operators with 2 quark currents and 2 lepton currents. And there's a triplet. When you have a doublet fermions, you have a singlet field and you have a triplet field. And in each process, they enter as a specific combination. It's either C1 plus C3 or it's C1 minus C3. And the top line here, this is top physics. In fact, for a future collider, for instance, CLIC or an FCC type electron-positron collider, so you're colliding electrons and you are producing TT bar pairs, you're probing a Wilson coefficient in this minus combination. So it's singlet minus triplet. Whereas when you study the B anomalies, which you see in B to S, L plus, M minus, you're probing the orthogonal combination, you're probing C plus. So it means if you have a possibility to constrain these operators in a unified analysis, you will make progress because you will be able to remove flat direction. Okay, and there's more to this. So the situation as of now, LHC, not just LHCb, Atlas, and CMS. So I just wrote LHC. They have these wonderful angular analysis precision tests of the flavor sector and with B2S mu mu, and that puts a very strong constraint on this plus combination. And there's something that we will be seeing in the I would say in the near future. In the Bell 2 experiment, they are expected to observe B2S modes into dineutrinos. And when you have not the charged leptons here, but the dineutrinos, so it's another SU2 combination, you actually probe C minus, okay? But at the moment, this is just an upper limit, okay? But this is to be expected, so this is nice. And then, of course, if you have an E plus, E minus machine that studies TT bar production, you're really probing C minus. So they are all linked, but of course, when you do TT par, you are probing 3rd generation fermions. And when you do B2S physics, you are probing 1 3rd generation fermion and 1 2nd generation fermion. So you need a link to connect these Wilson coefficients, and that's a flavor link, okay? And it comes at the price that there's some suppression, and we will be talking about that. I'm also mentioning here lepton universality, and that's a big one, because one of the anomalies that we are seeing right now that everybody is so excited about is about a possible difference between muons and electrons that's bigger than just their mass. So ideally, you would like to do a SMEFT fit just with muons. That means if you want to study here TT bar production, of course, you would need a muon collider. Okay, so so in principle, you would need to either assume universality to combine these data, but or you would need to have more than one collider. Okay, so at the moment we just make some assumption to make here progress, but it is clear that in the future you have to do lepton specific fits. Okay, so how do we make a top-bottom synergy explicit? Well, we consider 11 dimension 6 operators from the Warschau basis in our fit, and these are penguin operators, these with a covariant derivative and 2 Higgses. We have dipole operators, those are connecting quark doublets with quark singlets, and then gauge bosons, and the semi-leptonic 4 fermion operators. And these are really the important ones because they are connecting really, I mean, these are supposedly the origin of the flavor anomalies in the B sector. So if the B anomalies are correct, then we are seeing new physics in these Wilson coefficients from these certain or combinations of these semi-leptonic 4 fermion operators. So they are really, we're at the key of these anomalies. So we would really love to connect them to top physics. And of course, if you look at these 4 fermion operators, you understand quickly it's a bit of a mess. They have 4 flavor indices. This was exactly the topic the previous talk. For instance, this one here, the singlet operator, there are 2 lepton flavor indices, K and L, and there are 2 quark flavor indices, I and J, and they each goes from 1 to 3. So this is an enormous tensor. To make a fit, one has to do some assumptions to go on. Okay, and if you have more data, you can relax these assumptions. But this is what we did. So for the quark flavors, they're just 3 pattern. So you can combine left-left operators, which is here, or also in the 4 fermions, okay? Or you have right-right operators, or you have chirality flipping operators, left-right. Okay, so these are the 3 structures. And we considered something very simple. We considered a top or beauty-philic pattern. So we only switched on for the quarks the 3-3 element. Okay, and to make this a bit more visible, I'm restraining myself here to 2nd and 3rd generation only. It means that we have a Wilson coefficient. This is just the quark part of it. Okay, and with flavor indices I and J, and we say, well, everything's proportional to the 3-3 one, and just the 3-3 component is switched on. All the others are negligible. Okay, and this is what we assume for all 11 operators for the quark part. Only the 3-3 element, so the top or the beauty one, is switched on. So of course there's flavor mixing, and this is our assumption is in the gauge basis. And when you go to the mass basis, and we have to do some flavor rotations that affects, of course, only the left-handed fields, and then the Wilson coefficients of the operators with the left-handed quarks, instead of this matrix with just the 3-3 element switched on, there is the 3-3 element is still big because it's VTB squared, it's roughly 1, but you induce off-diagonal elements, okay? So the 3-3 element is what matters here for the top sector. It would matter for TT bar production. For instance, it's roughly 1. So blue is top and it's 1. And the BS anomalies, they require mixing between, I mean, some communication between 2nd and 3rd generation. It's an off-diagonal one. It's of the order, it's VTB times VTS star, and it's 4%. Okay, so when you have an order 1 effect in the top sector, it feeds down to a 4% effect in rare BD case. Okay, for the leptons, okay, I mentioned this already. Most of today's data is actually for muons, because muons are those that have the better reconstruction efficiency. So most of the data we have is for muons. Therefore, most of the results are already lepton specific. So if K and L are our lepton flavor indices, we can just set them to 2 2nd generation leptons. Okay, so but there's, however, one exception to that, because we want to profit from these dineutrino modes, B2S, nu bar, when B meson decays to a K-on or a K star. And these modes, they are not lepton specific. I mean, on the contrary, they are an incoherent sum of branching ratios into the individual lepton flavors. Okay, so the flavor is not reconstructed. Instead, it's the sum over the flavor. And of course, it matters for the sum what you assume for the flavor structure. If you are assuming that lepton flavor is conserved, there will be no off-diagonal contributions. If you are assuming lepton flavor is universal, then this will be a Kronecker dense tensor in flavor space. Okay, so once you're including these dineutrinos, you have to make some assumption, and we assumed universality just to make progress, but of course you could do something more sophisticated. So that means in these semi-leptonic four fermion operators, we assumed actually that they are universal, so there's just the unit matrix in flavor space. Apart from this dineutrino mode, this is a very mild assumption because essentially the data are already lepton specific. But of course it means when we go on and in particular when these B anomalies, the hints for violation of universality, when they get strengthened, it would be really desirable to perform fully lepton specific fits in terms of EE, mu, mu, and ideally even tau tau operators and perhaps even lepton flavor violating ones. Okay. So this is what we know a bit of the sketch of our synergies. We scan 11 Wilson coefficients at the TV scale. Then we use one loop RGE to the weak scale. We match onto the weak effective theory. We compute all the B observables, and we use many tools, Flavio and Wilson. And we confront everything to data, and we do a fit with the EFT fitter tool. So again, here are our 11 Wilson coefficients, and in color-coded boxes, we see by which data set they are actually constrained. So there's a box in red that's accessible with top physics, TT bar production at the LHC. There's a small but important box here in gold on Z2BB bar. There's the B physics block, and in black we have the future electron-positron collider block. And the nice thing is there's kind of really, it's a complementary. So there are Wilson coefficients that are not constrained by, they are only constrained by one sector, but then there's something where the constraints are overlapping, so we get the removal of flat direction. Okay, so this was our goal, and okay, this is a bit more of a sketch, more of details what type of observables we considered. So these are our top sector observables, TT bar production, TT bar gamma, TT bar Z, the top widths, Z2BB bar. This is our B physics block. And again, in the last column here, I'm making note which process is sensitive to semi-leptonic four fermion operators. And this feature is only shared between B physics and electron-positron to TT bar production. Okay. So this is our top input, a little bit more for the details, everything you can read from our paper. And this is results. Okay, so to highlight our synergies, this is the fit to the top sector only. And this is data as of now. Okay, so we see that we get constraints on 6 Wilson coefficients within our setting. And the dipole operators, they are kind of okay constraints, and the penguin operators, the last 3, the constraints are not very good. Okay, but this is the situation as of today. So now we add beauty physics. Okay, and now we see that 8 Wilson coefficients are constrained, including 2 semi-leptonic 4 fermion operators. And that is this combination C+. This is what B physics can do, B2S mu mu constraints very efficiently, and another one. So the constraints here from B physics on these 4 fermion operators, they're very good. They're the best from this whole list. If you compare with the previous plot, then you find that this UB Wilson coefficient and including all the others here, the constraints have gotten better. And there's one sticking out, this phi u, this is still a mess. Okay, and to illustrate what we actually gained, this is a bit the synergy teaser. For instance, in the plot to the left, this is CUB versus CUW, and in light blue you see what only top physics can do, and in gray you see what B physics can do. And it's really, I mean, it's even visible in this plot, the constraints are orthogonal, and when you put them together, you're reaching these dark blue regions. So this is a significant improvement by doing things globally. Okay, so what is going to be expected in the near future? Well, in the near future, we are having the high luminosity LHC. So the precision will improve on top observables, and Bell 2 will start and probably determine the branching ratio of these dineutrino modes. And this is the situation what you expect, and in dark blue is shown where we are now, and in red we see what we can expect in the near future with the high luminosity LHC and Bell 2. And what you see is that instead of LQ plus and or LQ minus, you can resolve them both. Okay, so because that's just because when you put B2S mu mu and B2S nu, so the muons and the dineutrinos together, you get orthogonal constraints. So the red one is really much stronger constraints than what we have now in dark blue. And what you also, of course, see here in the plot to the left is these Wilson coefficients, they are not perfectly at their standard model value C equals 0. And that is because we are seeing at the moment a bit of an anomaly in these in B2S mu mu. And we assumed in our fit that the central value is as in LHCb data as of today, and we scaled the uncertainties down with the high luminosity LHC. Okay, so that can be resolved. So now we go even much further and we envision a click-like collider, an electron-positron collider with these type of settings. So it comes in stages with different center of mass energies and polarizations, and there are some luminosities to it that you can see in this paper. And again, you get complementary constraints on these SU2 combinations. So instead of C plus, you can constrain now very efficiently C minus. Okay, and that's only click. Okay, so this is already a future scenario, and you see click can do 4 fermion operators as expected. These 4 here, the last 4 constraints. And again, I mentioned if you have an electron-positron collider, these will be electron specific. If you want to do muon bounds, you need a muon collider, okay, or you have to do something else. And if you study E plus E minus to TT bar, you get combinations, you get very strong constraints, but you get only the minus direction. You get it for this for fermion operator, and you get it also for the Z penguin. So now you can put everything together. So this is a bit of our central result, which displays the synergies for the, in particular for the 4 fermion operators. So light blue is today and the future, the near future. So light blue is including Bell 2 and the high luminosity LHC, and gray is a click type collider, and blue is what you get when you combine things. So so clearly there's an improvement in all Wilson coefficients, but the improvements are particularly drastic here for the 4 fermion operators, for the semi-leptonic 4 fermion operators. And I'm highlighting them because they are playing a key role in present B anomalies, okay? So it's not just any operator, I think it's an operator that's particularly interesting given the experimental situation. And to look a little bit deeper into this CLQ1 and CLQ3 interplay, this is a bit of a movie. So the first line of plots is now. This is the near future with Bell, and this is the future with click. Okay, so what's shown Shown is a correlation between CLQ1 and CLQ3. So this is a 2D plot. So this is a 2D projection, and these are the 1D projections, okay? And you see today, we cannot really determine these here, okay? For the 2D projection here, we see, well, this is the star, is the standard model. Today, we know physics constrains very strongly the plus combination, CLQ1 plus CLQ3, and that's fixed. That means this is a straight line, but we don't know anywhere where we are on the straight line. And now comes Bell in the near future. So we start to put an orthogonal constraint here. And we see that, well, there's the standard model solution, and then there's also a BSM solution. Also note that the scale here, so here the Wilson coefficients go from -1 to 1, and here we are 1 order of magnitude down. So this is really zoomed in. When we go to the near future, we zoom in. Now we zoom even more in. Just look at the scale. And with assuming central values for LHCb and the design parameters for click, you see here's the standard model, and this is the best fit solution in this 2D projection. So the B anomalies, if they stay and just uncertainties shrink, and we add these complementary observables, this becomes very visible in the future fit. Okay, with that, I'm done. Yes, I talked about synergies between beauty and top, and they have been mentioned, to my knowledge, first quite some time ago in a paper by Zoltan Ligeti and Gilad Perez and friends, and it was clear that there is a link, because beauty and top, they live together in the same SU2 doublet, and when you have constraints on beauty physics, they should be relevant for top and vice versa. But it needed, I would say, some time to actually put this to work, and that of course also required sufficiently precise and rich data. And so now I think one can see that there's benefit in fitting things together. And in particular, this has been, I would say, it's beneficial for these semi-leptonic 4 fermion operators, because they are of importance, because they are at the heart of what we are seeing now in anomalies. And let me mention that there's an interesting CMS paper on that topic, and they're actually providing constraints on semi-leptonic 4 fermion operators. They are having a study from tops with leptons, and their bounds are weaker in the Wilson coefficients, where actually our fit already works. But CMS also probes Wilson coefficients, which we have not been able to constrain these days. So I think there is more room, maybe also for opportunities from the collider side, to consider constraining semi-leptonic 4 fermion operators. Okay. And yes, I think these global fits, of course, they have a sensitivity to flavor. I mean, you need to make some assumption about flavor at the moment to make progress, but that also can become a benefit, because eventually one would be able to maybe distinguish some assumptions about flavor, and that would of course require to broaden the flavor links. So not just top and beauty, maybe also other sectors. And of course, ultimately, the SMEFT tool is very rich. One can merge this with, if you have strong people with strong numerics, you can merge it with other sectors. Thank you very much.
Okay, thank you. Susanna, I'm sorry, but I'm going to have to ask you to direct your question to the Slack server, because we're running a bit behind now. And thanks for your talk, Gudrun. Can we just jump on to Sebastian's talk?
Yes. Can you see my slide?